Hi guys, welcome to the channel. Today we're going to be looking at differentiating the sum of two vectors. This is one of these results that is fairly basic, but comes in handy quite a lot. So we're going to have a look at it. We're going to have a look at it and then prove it. So the result itself, let's start by defining our vectors. We'll call one vector r, and it will be time dependent, and we'll make a second time dependent vector, t. Okay, and now we're just going to ask ourselves, what would happen if we take the time derivative of the sum of these vectors? So d by dt of r plus s. And we find that this is equal to, very simply, dr by dt plus ds by dt. Oh, that's not a t. Oop. Okay, and that's fairly simple. It's literally just almost distributive in this case, that the sum of two vectors, you're just taking the differential of dr of r and s and adding them together. Okay, now let's have a shot at proving this. I can draw a straight line. Not quite straight, but we'll go with it. Okay, let's look at the proof of this. So first things first, we want to kind of accurately define what we mean by differentiating. And what I mean by this is that I'm going to say that dr by dt, the differential of r, which is dependent on t with respect to t, is equal to the limit, that's lim, of a small change in the time, delta t, as that small change goes to 0, of r at t plus a small change in time, minus r at the original time, t, all over the small change itself, delta t. Now, this is how we're going to define the differential. And using this definition, we can apply this to the second part of our above equation, this part here. We are going to apply this definition to this. So let's get started. Now, applying that same logic, we are going to say that the limit of delta t as it goes to 0 of, well, actually, we can first of all show that that this r at t plus dt minus r is actually just the same as small change in r over the small change in t. So using this as well, we're going to say the limit as the small change in t goes to 0. Up here, it'll be a small change in r over a small change in t plus a small change in s over a small change in t. And essentially, this is asking what's the behavior of this change? How does it change immediately after a small time interval has passed? And this time interval is infinitesimal. It's tiny, so it is an immediate change. And what we can do here is, as you can see, the bottom of both these fractions is the same, so we can rewrite this as the limit. You're going to have to completely excuse my god-awful writing. As the limit of delta r plus delta s all over delta t. And using this, we can simply take delta t on the outside. You're also going to have to pretend that's a delta. 1 over delta t of delta r plus delta s. Now, let's compare this to our original definition up here, where we said that dr by dt is equal to the limit as delta t goes to 0 of this small change over t. So taking dt out, we can see that the delta r, goes to dr. And that's in the case of both of these here, where you can rewrite this finally as d by dt of r plus s. And that's it. That's the proof. Fairly simple, nothing too complicated to it. One of these results that, you know, maybe if you're coming up to your exams at this point and like a few people haven't actually bothered to look at this stuff in like a year, then yeah, this is going to be useful for you. And it's going to be useful for you down the line, especially if you're studying physics. This tends to come up all the time. Yeah, so with that, I'm going to leave you. And, if you want to help me out, new channel, like, subscribe, all this stuff, according to YouTube analytics, blah, 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 blah. Yeah, you get it. Anyway, thanks for watching. See you next time.